Okay, so HEC-HMS Modeling Bootcamp, what that means is that this will be very interactive and very hands-on. It's there will be lecture, but it's primarily going to be a lot of time on the hands-on workshops so that everybody can get experience using the model. So my company, Watearth, I started it in 2008. We're a water resources firm focusing on hydrology, hydraulics, and other water resources topics. Again, if you have questions after today and tomorrow, you're more than welcome to send me an email, and I'll either get you answers to it or help point you in the right direction for resources. Okay, so our agenda, we're going to start out with an introduction, cover hydrology modeling methods, and then an intro to HEC-HMS, kind of some basics, some model demonstration, looking at rainfall data, base flow. Some of these items, we're going to cover them to be comprehensive with basic HEC-HMS computations, but frankly, you might not use them in most of your projects like base flow, but just want to get you familiar with it. Loss rates, different types of losses like green and amped, which is used, for most of the projects, at least within Harris County. Those of you who are up in North Texas, you might be more familiar with like the SCS curve number method. Unit hydrographs, different methods for that, stream flow routing, and then reservoir routing, which also applies to detention basins. So HEC-HMS now has some pretty decent capabilities in terms of outfall structures and tailwater that it didn't previously have. We'll look at diversions and sources, which can be helpful if you have overflows between watersheds, or maybe you do detention routing in a different model like ICPR or pond pack, and you want to incorporate the hydrograph back into HEC-HMS to check for impacts in the watershed. So you would do that as a source gauge. There are other reasons you could use a source gauge, but we'll get familiar with that. And then we'll kind of wrap up tomorrow with a comprehensive project, and then also an overview of some advanced topics. All right, so of course HEC-HMS is a hydrology model. It's basically sponsored and developed by the U.S. Army Corps of Engineers, and because they are a federal governmental agency, they typically are only responding to requests for new features that are put out by other federal agencies that request it. Sometimes they'll do custom programming, but usually it's to enhance the capabilities for governmental use. But it's a great model. It's free. They're always coming out with updates. This course will be focused on version 3.3 because most of you are doing projects in the Harris County area, but everything that you learn will apply to the more current version. So it's now at version 4.2.1. The reason why it's important to kind of keep up with the versions is if you are doing like a project that's going to be submitted to FEMA, it's usually best to keep it in that same effective model version. And then also certain public agencies will require specific versions. They don't always, it depends on the criteria, but like the Harris County Flood Control District wants to see the submittal in the same version as the effective model, as long as it has some FEMA component. If you're just simply doing like a detention routing model and there's no FEMA submittal, then you can kind of pick and choose which version to use. So basically it's hydrology focused. It has some light hydraulic capabilities in terms of like outfall structure computations for detention, and it will do stream routing, but it's hydrology based routing as opposed to hydraulic or unsteady flow or dynamic routing. So HEC-RAS is kind of the companion model, and that's the hydraulics model focused on open channel flow. And now the latest version not only offers one-dimensional flow, it also offers two-dimensional flow modeling within the unsteady flow component. So there's other HEC Hydrologic Engineering Center programs as well. So the reason that you would use HEC-HMS is, exactly what everyone stated. It's usually project-driven. You might use it because that's what the criteria requires. You might use it because you have an option of models to use, and it's a fairly easy model to use. But we use it for both planning level studies and design level studies. So documentation wise, if you go to the HEC website, there's a user's manual, there's a technical reference manual, and an applications guide. So the applications guide is basically example projects. The technical reference manual sometimes helps to dig in if you've got questions that you're trying to resolve and need further detail. The user's manual is typically more just focused on how to. So if we, let's see. So basically, if you just Google USACE for U.S. Army Corps of Engineers, HEC, pulls up the Hydrologic Center homepage. And you can click on the HEC-HMS. So it's got the latest version, 4.2.1 here, but if you go to downloads, and we'll look at this a bit later, you can see there's a lot of archived versions on here in case you need to go back and use an older version. And you can also click on release notes and get information about what's changed in that particular version. And then documentation. This is where you're going to get users' manuals to go with various versions of the model, or the application guide, which is not updated quite as frequently. And then you've also got the reference manual, which is a little bit older, but it talks about the computations behind it. All right, so some hydrology fundamentals. How many of you have had a hydrology class in school? Yeah, I mean, pretty much it's going to be required. But so HEC-HMS is just basically based off of those hydrologic fundamentals and principles. So we'll talk a little bit about the processes that get modeled. So in the hydrologic cycle, of course, everything driven by the sun or the solar energy. Typically, when we model in HEC-HMS, we tend to be most focused on the rainfall, the infiltration that's occurring, which is a function of both the soil and the land use or impervious cover or amount of urbanization. And then ultimately, we're trying to calculate the runoff, both in terms of peak flow and maybe volume or shape of the runoff hydrograph. Evaporation or evapotranspiration, if you're doing continuous simulation modeling, you may include that as well. But for design storm events, it's typically rainfall, infiltration, and runoff focused. So newer versions of HMS do also have capacity to incorporate interception by tree canopy. But again, that's more of like a long-term model than a design storm event. So most of the work, frankly, is going to involve design storm events, which are synthetic events based on statistical analysis of actual rainfall or historical data. Historical rainfall would be more like gauge data if you want to either model, say, 10, 20, 30 years of record rainfall, or maybe you just want to calibrate to a specific historic rainfall event. Tropical Storm Allison, a lot of things were calibrated to that back in 2001. But so if you have your model set up and you're trying to calibrate it, so then you get the gauge data and you're trying to match either peak flows, or if you're also doing a hydraulic model, you might try to also match water surface elevations. All right, so average annual rainfall. So what's your average rainfall in Dallas?
The yellow.
The yellow. Okay, what is the yellow? About 40, 45 inches?
It says 25.
It says 25, okay. Do you guys work in Fort Worth or any place further west, or are you pretty focused on Dallas?
Pretty focused on Dallas. We'll kind of go up north more, northeast more,
okay.
Dallas.
Okay. Yeah, and so Houston area, it's going to be more like 45 to 50 inches per year. But in terms of design rainfall data, so there's different sources. Some of the sources like TP40 have been around kind of forever. and they're a little bit, I guess, outdated per se. So Texas has a USGS publication that's been more specific and more recent with rainfall data. But you can reference other sources if you need extended longer-term durations. So this is from TP40. So if you look at Harris County, I think it shows about 12 inches for a 100-year, 24-hour rainfall event. But if you look at more recent data from the USGS publication that's been incorporated by the Harris County Flood Control District, you'll see that it actually varies by watershed, and some watersheds are a little bit more than 13 inches for that design storm event. So some of these NOAA publications have been updated for various states if you end up doing work outside of Texas. So the USGS publication that I'm talking about also included New Mexico and Oklahoma updates. Okay, so our design storm events, they'll have a depth associated with them. They'll also have a duration. Typically we're looking at 24-hour events, but you might need to look at a longer term event, a 48-hour or 72-hour at some point. The shorter duration events tend to be for a little bit flashier storms or specific reasons. And then a frequency. So the 100-year being equivalent to the 1% or 1 in 100 chance of being equaled or exceeded in any given year. And so the 2-year is basically a 50% or a 1 in 2 chance of being equal or exceeded in any given year. So if we have a 100-year event and my house floods, does that mean next year I'm fine and don't need to worry about it? Yeah, so we all know that, but the general public doesn't always. Like, I had a older friend who flooded during Tropical Storm Allison, and pretty deep in the White Oak Bayou floodplain, and it's like, are you going to sell your house and move? Oh no, I've flooded. I'll be fine now because it's 100-year event.
Does that person live in Jersey Village by chance?
No, in Timber Grove area. But yeah, I think that's pretty common, and then we see like apathy kind of set in after it's not raining or it's not flooding anymore. Okay, so just the depths obviously vary around the country and around the state for the various rainfall events. And then it's interesting to me to look at like a 4-inch event and just see like where is that a 2-year event, which is about what it is here in Houston, or where is that almost getting up to like a 50 or 100-year event. Okay, so in the design storm events, so we have a depth, we have a duration. We also need to have a peak center, like where is the peak rainfall occurring? Usually that's like halfway through or 2/3 through. And for projects in Harris County, you're going to use like a 67% peak center, which just basically means that the peak rainfall is going to occur at about between hour 16 and 17. If you're using the SCS unit hydrograph, then you kind of select the type based on where it's going to occur peak-wise. And this graph gives you an idea of, for the SCS, where to use which type event. And again, that's going to relate to where the peak center occurs. All right, so losses, typically our largest loss in design storm events is going to be infiltration. If you're looking at longer term events, the evapotranspiration and interception can play a role. All right, so infiltration is really going to be driven by the soil types, but also the amount of impervious cover or the land use. So in the HEC-HMS model, we reflect urbanization or development either by percent impervious cover or SCS curve number primarily. And I'll say this again because it's important. If you're using the curve number method and you go from undeveloped to developed, you only want to change the curve number. You don't want to change the impervious cover too, or it kind of double counts it. All right, so our runoff hydrographs, they're a really great visual to tell us what's happening in the watershed. It's a depiction of what happens over time with the runoff, and it also gives us a feel for how the volume reacts in time as the watershed drains out. So there are various factors that influence both the shape and the volume, depending on urbanization, shape of the watershed, slope of the watershed, and so forth. So in our runoff hydrograph, we have the peak flow, and then we also have the shape of the hydrograph. So this is probably a 24-hour event. Most of the runoff has happened by hour 24. It's relatively spiky. It's not very slow to respond. This means, maybe it's clay soils, maybe it's pretty developed. If it was more undeveloped or conditions or a very large watershed, you might see the hydrograph squished out a little bit or flattened. The other thing that's important is the volume under the curve, or the volume of runoff is the area under the curve. And so you can simply calculate that. Well, the model will tell you the volume, but you can also calculate it in a spreadsheet just on a time increment basis of time versus peak flow, and just take an average or time versus flow at each time step. All right, so the watershed size and shape, obviously if we have a watershed that's like 100 square feet, it's going to respond really quickly. If it's 100 square miles, it's going to be much slower to respond for the hydrograph to get from the upstream end to the downstream end of the model. And then also the rainfall, the storm event. All right, so the time of concentration, is everybody familiar with time of concentration? Okay. So it's basically, you've got different types of flow paths within the watershed. And that time of concentration, or travel time, if you will, is going to be based on the slope, and it's going to be based on what the water's flowing through and over. So if it's flowing through a forested area, it's going to travel much slower than if it's concentrated within a storm sewer system. The time of concentration then is based on the longest flow path. The longest flow path isn't necessarily the longest line following the slope, it's the slowest travel time. And it's essentially the time required for all points in the watershed to start contributing to the point where the hydrograph is being developed. So, if we look at some really geometrically conceptual watersheds, it's not always a straight line. It may be kind of meandering, but you get into transportation projects, and sometimes if you take the longest flow path, if you have an odd-shaped drainage area where you have a road, but then it drains into a larger area, L1 may not necessarily be representative of the bulk of the watershed. In this case, you might be better off breaking it into two sub-areas and having a linear upper sub-area and then more of a square lower sub-area, or you can look at whether L2 is more representative. All right, so when we do longest flow path computations, we look at the node where the hydrograph's being generated, in this case these kind of purple or blue nodes, and then look at the travel path. And some of these are fairly linear. They're following channels, they're following really specific flow paths. Some are less linear, where you've got kind of an upper one, you've got a little more overland flow occurring. What's interesting in this lower area is that it's a very large drainage area, but it's also an area where ponding occurs. And in a HEC-RAS unsteady flow model, it's being modeled as a storage area. So we really don't need the longest flow path like all the way to where the storage area drains out. We actually just need to get it into the storage area. So that's why it's kind of hanging out here in the middle of nowhere. And if we look at like a hillshade of elevations, so initially in this project, the longest flow path was taken all the way to the outlet for this pond, and the hydrograph and the results just weren't ending up being reasonable compared to like historic events. And so then we started looking at, well, we really just need the hydrograph to contribute to the ponding area, which basically starts at this point. So the flow path was shortened pretty considerably. So we do have to analyze the hydrographs and look at the results and make sure that things are reasonable, as opposed to just, well, this is what the model said, so it's correct. So sometimes it can be a little bit iterative. All right, so the volume of runoff is influenced by similar things that the shape of the hydrograph are influenced by, but obviously infiltration, level of urbanization, and then soils types are really going to drive the volume of runoff. So let's look at some hydrograph operations. And some of these you can do by hand if you wanted to, but they're done within the HEC-HMS model, and they're actually really easy and, to me, kind of fun to visualize. If you look at combining hydrographs, does that make sense shape-wise and like peak flow-wise? So a combined hydrograph just basically takes two or more hydrographs and adds them up. And what it does is it adds each and every time step so that you have an accumulation of the hydrographs at that time step. Now, you wouldn't do that if you have a hydrograph like 5 miles upstream and 5 miles downstream. These are hydrographs that are various drainage areas contributing to the same node or junction, if you will. All right, so all of the hydrology models essentially will do this. Again, you can easily do it in a spreadsheet to add them up. But basically, so if we have HEC-HMS results for a specific junction, we've got two hydrographs, and they both flow into a junction, and then they combine and flow out. So if we just take the very bottom number, you can just check it, 0.55 plus 2.85. Yes, that equals 3.4. So it's you never just add peak flows. It's really the combination at any point in time. So the peak flow from the combined hydrographs might not be the peak flow of 1 plus 2, unless they happen to have their peak occurring at exactly the same time step. It's generally going to tend to be like a little bit less. All right, so our combined hydrographs, so we have hydrograph 1 in red, hydrograph 2 in gray, and they combine to form hydrograph 3. In this case, the peak is occurring at a very similar time, so it may be close to adding up the two peaks. But you can just visually look at it and say, yeah, that makes sense. If you take hydrograph 2 and stack hydrograph 1 on top of it, the shape looks reasonable. You can do the same thing with 3 or a lot more hydrographs. Again, just looking at the time steps and adding up the flows. So in this case, you've got 3 hydrographs combining, and here you can clearly see the timing is different. So it wouldn't be correct to add a peak from the red plus a peak from the turquoise plus the peak from the gray. The combined peak of the blue is something less. And if you draw like a vertical line down from the blue combined peak and see where it hits the hydrographs, you'll see that the combined might be close to the peak of the gray, but it's not picking up all the peaks. So hydrologic routing, there's standard reservoir routing, which we'll talk about, which gets used for detention routing. Hydrologic routing is used for stream flow routing, and we'll go through several of the methods that are used. We'll talk more about detention routing tomorrow. So stream routing is an important process, especially when you have flatter, less developed watersheds, but flat slopes definitely. What it does is it accounts for travel time. So if you're going 500 feet, you're not going to see much attenuation, lagging, or dampening of the hydrograph. But if you're traveling, let's say you're in a watershed like Clear Creek. I know you guys do a lot of work on Clear Creek. There's very significant lagging and attenuation of the hydrograph that occurs. And what that means is attenuation is like a dampening of the peak flow where it comes down. And lagging is just that the amount of time that it takes to travel from one point to another. Generally, the runoff volume is not going to change. It's going to stay constant. Now, if you have a system where you have a lot of infiltration losses, you could see a change in the runoff volume. But generally, for the type of systems we're talking about, the runoff volume stays pretty consistent. So the wider the floodplain, the more floodplain storage, the more resistance to flow. That means the higher Manning's N values in the overbank, even the higher Manning's N values within the stream itself. More of a forested, highly vegetated condition. It's a lot rougher. The water's going to move a lot slower. So we see more storage, more attenuation, and more lagging. So basically, in HEC-HMS, so we've got our little drainage subareas with the green. Both contribute to a junction. The upper area is routed, in this case, just through a roadside ditch, to the lower area where the two hydrographs would combine. So what we end up with is a hydrograph with a 98 CFS peak from the upper drainage area. It gets routed through that roadside ditch. The peak attenuates to 78 CFS. You can see it kind of dampens and squishes out a little bit. Gets combined with the downstream area in red, yielding the blue combined hydrograph. If we look at a lagging example, we've got a 93-acre site with the hydrograph contributing at a point on the south, basically southern corner. And then that hydrograph needs to get routed to the pink node within the drainage channel. So I think in this case there was no detailed survey data on the ditch, and it's not super long, but we wanted to account for the travel time, and so just the lagging method was used with an estimated slope and velocity, and so it was lagged 90 minutes. So that's a hydrograph routing option you can use in HEC-HMS. It doesn't change the shape, it doesn't change the peak, it just basically picks it up and shifts it in time. And the reason that might be important is if you're trying to look at downstream effects of the hydrograph and the timing. All right, so hydrograph analysis is kind of fun to me, but basically you analyze the hydrographs and evaluate what's going on. Does it make sense? What's the peak telling us? What's the shape telling us? As the hydrographs combine, do we expect this project to have an impact downstream? So each hydrograph really tells a story of the watershed or the sub-watershed that it's representing. Yeah, so if we have the tortoise and the hare, which hydrograph is going to be faster, the tortoise or the hare? Any guesses? I know it's not that early. All right, who thinks the tortoise is going to win? All right, nobody. Who thinks the hare is going to win the hydrograph race? Okay, yeah. So the hare is going really fast, and so you kind of expect that the hare is going to get there first. But then the hare actually stops off and gets coffee and tea and visits with friends, and then I think in the end the tortoise actually wins the race, if I remember the story right. The hare would represent things maybe the hydrograph's going to go through a detention basin. So it may be a really steep watershed that's moving fast, but it goes through a detention basin, which then basically lags and attenuates the hydrograph. It might go through, this is kind of outside the scope of this seminar, but if you have low impact development features that the hydrographs are going through, it'll tend to slow things down. So the tortoise is pretty slow and steady. Maybe it's kind of a flat watershed, whereas the hare is a little bit erratic. It's moving fast, but then stopping and going through various features. All right, so if we look at, we'll just go through a few hydrographs here. Which one of these represents, which one of these hydrographs would be developed conditions for the same site? The pink one, yeah, because it's spikier, it's got a higher peak flow. So larger drainage areas, obviously the larger hydrographs. It's the same project, so all the other considerations are similar. So which one's the 10-year? The red one, yeah. But, so you can see the shapes are pretty similar for the two events. It's going to have a similar rainfall distribution pattern, and that's what's going to drive the shape of the hydrograph, as well as the characteristics of the drainage area. All right, so a short TC versus a long TC. Which one's the shorter TC? The pink, yeah, so it peaks a little bit sooner, but you'll notice that there's not a huge difference, at least on this scale, between 0.27 hours and 1.5 hours. So the TC makes a difference, and it makes a little bit of difference in the peak flow. I don't recall where this particular project is. It'll vary a little bit from location to location, but the peak flow is actually the time that occurs is really driven by the peak center of the rainfall. So you see some differences occur by TC, but when you look at the hydrographs, even if you have a 10-minute TC, you're not going to have the peak of the hydrograph at 10 minutes on a design storm event. It's going to occur somewhere closer to the peak center of rainfall, just based on how that occurs. Now, if you're using like a rational method or something that's not design storm based, you may end up with, you'll see peaks happening earlier on. But when we're looking at design storm based, where the distribution is set over 24 hours or 6 hours, then that peak rainfall is going to be pretty controlling. All right, so which one of these would be the 33% peak center? The pink one, yeah. And like what design storm event, like duration, do you think this might be?
Or you mean like?
Yeah, like the amount of hours of the storm.
3 hours? I don't know. That's.
Yeah, I'm gonna guess it's probably a 6-hour event. So it's very watershed driven, but you don't see. So this peak center in blue is at 67%. So it's about at hour 4 or so. So that kind of tells me that it's a 6-hour event, but you still sometimes have, it depends on the watershed, it depends on the soils, the size, the level of impervious cover. You might still have a little bit of runoff occurring after the end of the event, and we would expect that in bigger watersheds with flatter slopes. Like this is, the peak flow is like 300 CFS, so it's not a huge watershed. All right, so 12-hour versus 24-hour duration. Which one's the 24-hour duration storm? The green, yeah. And then Baltimore versus Houston. Which one do you think is Houston? The blue, yeah. Yeah, because a lot more rain. Okay, so we've talked about the hydrologic cycle and all the various operations, and you'll have a chance to work through these within HEC-HMS. Are there any questions at this point before we jump into HEC-HMS itself? Okay. So let's go through some HEC-HMS components. It can be used for a lot of different things. I mean, just to generate peak flows and runoff hydrographs, to do detention routing, downstream impacts analyses, flood insurance studies, and so forth, generating peak flows to use in HEC-RAS or other models. Let's look at a project example. This is 24 square miles. It's basically inside of a levee system. It did include HEC-RAS on steady flow, hydraulic, and storage routing, but we're going to focus on the HEC-HMS portion. So there's various drainage areas with sizes ranging pretty considerably. Each drainage area contributes to a specific node within the channel system, except for the ponding area, which you'll see is huge, like 4,800 acres. That basically is modeled as a storage area in HEC-RAS on steady flow, and so routing is actually done through there to route the hydrograph and lag it and attenuate it into the drainage channel. So the HEC-HMS model looks something like this. you'll see some drainage areas aren't really connected, and that's because there's no like routing reach, and that's because this model's not being used to do any type of watershed impact analysis. It was developed from scratch and just intended to generate hydrographs to be used within HEC-RAS on steady flow. So there's some pump and weir, so you can put simulate weirs as diversions within the model. You can also, in this case, the pumps were modeled as a diversion. Storage areas, some reservoir routing was done within this model, even though HEC-RAS on steady flow was used kind of for the main channel and pump stations. So you can see the individual hydrographs. The peaks vary considerably based on the size, and you see a little bit of change in the way the shape looks, primarily dependent upon the level of impervious cover. Some of the hydrographs were routed over land. Some had diversions and other things occurring. And then you can start combining them. And what I like, so like this turquoise hydrograph combines the pink hydrograph and the navy blue hydrograph. So you see the turquoise basically follows the pink to the peak, follows the receding limb, and then kicks up when the blue hydrograph, navy blue, starts contributing, and then it's, for the rest of the duration, pretty much higher than the pink hydrograph. Storage areas, I believe, yeah, this came out of HEC-HMS, but you can see they're kind of filling up, and they're not really draining out in 48 hours. If we want to see them drain out, we'd have to extend the model out longer. This is in the Lake Jackson area, pretty significant rainfall events, very, very, very flat, really slow drainage time. Just to kind of orient you, this is the HEC-RAS on steady flow layout. And so pump stations were modeled, different direction flow within the main channel. But in order for this to work, all of the hydrographs had to be done in HEC-HMS and incorporated in. And then the results show, in this case, flow going in two directions. It was used to upgrade and size pump station improvements. So these staged hydrographs were actually generated in the HEC-RAS steady flow model. And so this red is the huge, like almost 5,000 acre ponding area. So it fills up, and again, it's taking a long time to respond and drain out. The sad thing is development was starting to occur in that area, and I suppose, you know, homes are being built to standards with specific finished floor elevations, but it wasn't within like a mapped floodplain. So floodplain storage is starting to be taken up and things like that. Now, eventually, the results of this project did get incorporated into some map upgrades. So that's a good thing. Various water surface elevations. So a lot of times we're not going to calibrate projects, but we can kind of validate the models if we have data to compare to. So in this case, the 100-year event was almost 14 inches. Historical data on Tropical Storm Faye, which was 10 inches. At two locations we were about a foot higher, which seemed in the order of reasonable given the differences in rainfall. One location, it was very similar results. So this is what it looked like before the study, with the entire interior levee system just mapped as being out of the floodplain, which it was out of the floodplain of the flooding source, but there's still interior floodplain. So the results of the study show inundated areas in blue, which previously were not shown to have flooding risk. Okay, so HEC-HMS, we've talked about a lot of the capabilities. The reservoir routing is done with modified pulse, which we'll talk more about tomorrow. So in setting up the model, we're always going to have a subbasin. And you may have a model where the only thing you have is a subbasin because you just want to get a hydrograph or a peak flow for that one drainage area. And then from there you can get, as complex as needed. Anytime you're going to combine multiple elements, you'll have a junction. Reaches are used to route flows from an upstream point to a downstream point. You can also have a subbasin contribute directly to a node with no routing. So those are options: detention basins, sources, diversions, that type of thing. All right, and then the results are going to always show our hydrographs. It'll show all of the hydrographs at that particular junction. So it'll show what's coming in and then what's going out once it's combined. And then in this case, this is a graph from a reservoir. So it shows the stage and storage hydrographs for the reservoir in the upper part. All right, so again, we're going to do the hands-on workshops in version 3.3. If you're primarily going to use a different version, like in Dallas, I don't think a version is specified. You could do the workshops in a different version. You might get a different answer than those doing it in 3.3 because they fix bugs, they fix computation methodologies, they tweak things around. So you don't always get the exact same answer. And if you've used HEC-RAS, you'll notice that as well. If you and that's one of the reasons for staying consistent with the effective model version for anything that involves FEMA, because you're not always going to exactly match results. But version 3 plus basically added in better detention routing, better reservoir routing, better outfall capabilities, better information on pumps, culverts, orifice openings, outfall structures, and so forth. So the computations on the outfall structures from the detention basins are more similar to like HEC-RAS culvert calculations now. So there were a few changes in version 3.3. If you want to know what happened in version 3.3 versus 3.4 versus 3.5, if you go to the Army Corps HEC website and you go to the downloads, each version will have release notes. So you could read and see, well, what exactly has happened between 3.3 and 3.5. Version 4 plus generally incorporated water quality elements that weren't in there before. The water quality elements are really related to, they're not related so much to things like you want to do a stormwater BMP. They're really related to pollutants that are generated off the watershed. And it's set up in a way to be able to integrate with HEC-RAS on steady flow, which has some water quality capabilities focused on the stream. So like temperature, nutrients, sediment, and so forth. All right, so our basin data, this would be for detention basins. We'll always have like some type of tailwater condition, whether it's a stage hydrograph, fixed or fixed stage, elevation volume data. So our model capabilities, again, so it's accepted by FEMA. Most review agencies are going to accept HEC-HMS, whether they require it or not. If you're working with the SCS curve number method in North Texas, HEC-HMS is one model you can use. You can also use like TR55, maybe TR20. A lot of models, including like EPA SWIM, do incorporate the curve number method. If you're working in Harris County, HEC-HMS is the model, and there's very specific methods that were developed for Harris County by the Flood Control District based on really calibrating historic gauge data. So when we get into unit hydrographs, there's actually a very specific Clark unit hydrograph method with equations and parameters developed for this area. Okay, so some limitations. It's not a hydraulic model, it's a hydrology model, so anything that's hydraulic focused is going to be more approximate. When we do stream flow routing, anytime you have like flat slopes especially, maybe moderate slopes, but definitely flat slopes, unsteady flow or dynamic routing is going to be more accurate to account for backwater conditions and those super flat slopes. If you have complex outfall structures, Those are more difficult to model in HEC-HMS. And the water quality components, again, doesn't really include like stormwater BMPs. But for a hydrology model, it's a really good model, and it basically accomplishes what needs to be accomplished hydrology-wise. All right, so has anybody, I think everybody in here is almost too young, but has anybody used HEC-1? Have you heard of HEC-1?
Yeah.
Yeah, it was a little bit confusing because you can't really visualize things. But if you ever have to go back to a HEC-1 model, HEC-HMS has capabilities to import it in. All right, so the way the model is set up is it has these different components, and it's not like super integrated communication-wise. Like you kind of have to tell one component, hey, you need to talk to the other component and have your data hooked up. That's probably the least intuitive thing about it. But all the models are going to have like a basin model. That's where we put in our geometric data and physical characteristics. They'll all have a meteorologic model. Primarily that's going to be precipitation, like your design storm event. But if you want to have gauge data from an actual historic event, you would incorporate that there, evapotranspiration data, and so forth. And then they'll all have a control specification. The control specification says, hey, model, this event's going to run for X number of hours, and here's my time step. There's also this kind of paired data where you enter data in the basin model, but sometimes you have to go to a different place and say, okay, here's what the curve looks like, and then the basin model has to reference that curve or use such and such stage hydrograph. So it's just incorporated in a couple different areas. All right. Yeah, there's DSS files, which some people like to work with. Depends on how complex you get with things. The DSS files or data storage files can actually be paired with like HEC-RAS to pull hydrographs in. And that works pretty well as long as the files are in consistent places. But if they're not in consistent places, there can be issues with it getting updated. All right, so all of the usual hydrologic process suspects are in HEC-HMS. We've got our graphical user interface. So pretty much, so it's kind of looks like a Windows file folder setup, if you will. But so basin models, again, that's going to be all of your geometry, your physical data. Meteorologic is the rainfall. Control specification says we're going to run for 24 hours, and here's the specifics. Now do it. Time series data would be like your stage hydrograph, which you'd have elevations over like a 24-hour period. It would also be source, maybe if you have a source gauge, so you have a runoff hydrograph that you're putting in, that would go under time series. Paired data would be things like elevation volume curves that might apply to detention basins. And so a lot of times you can click on elements within the graphical portion of the screen and get data, or you can click on the folder on the left-hand portion and see the data there too. So again, paired data is going to be like tables. This is storage discharge. Storage discharge used to be used more with the old HEC-1 if people were doing detention routing in it. You can still use it, but now that there's outfall structure capabilities, I find it less useful. But some of the watershed models might have it in for specific reservoirs. So all of the basically physical processes and items that you can tie to a location are in the basin model. And so for a watershed, it can get pretty intense and pretty messy, and you've got to zoom in and look at things. Okay, our meteorologic model, again, rainfall data, evaporation data if you're going to use it. So the precipitation data basically you end up double clicking on these, and we'll go through it, but you have to open the meteorologic model and then add events. And then in this case, this is like a specified gauge data. But we'll get to practice with using that. Same with evapotranspiration. All right. Let's look at some specifics of how to create the models, and then we'll do a demonstration and then get you guys started on some hands-on workshops. You know, you might be working within a watershed model and it already has rainfall data and everything, and all you're going to do is add a drainage area and get a peak flow or make a modification for a downstream impacts analysis. You can also start your models from scratch and less frequently import from HEC-1. Yeah, I mean, so just like the HEC-HMS versions might not match each other, your results compared back to HEC-1 may not match. So it doesn't all import, but most of it does, and it's pretty straightforward. And then you just have to review the file and see what needs to be changed. All right, so to run the models, basically, you've got to have your control specification, and then we have to like select the model that's being run, and then there's like an exploding water drop. You can also, the little icon that you can use. All right, so the control specifications also get entered kind of on the left-hand side. And then when you look at results, the summary table, you can get kind of a generic summary table, you can get a detailed summary table, and this is where you'd have your step-by-step hydrograph for each location. The hydrographs, you can look at the hydrographs visually and so forth. So our global summary table, you know, is just you can choose units of inches or acre feet. So this is basically, if we're looking at like a downstream impacts analysis, we would want to copy out of the global impacts table. The summaries results, you know, for specific subbasin, just gives us a snapshot. A lot of times we're just looking at the peak discharge. We might not care what the hydrograph looks like. But it gives us the it gives us the time to peak too. And sometimes that's important when we start looking at, well, why is there an impact downstream, and what time are the peaks occurring, and it can be instructive to look at that. And then our detailed table with the time series step by step for each hydrograph location. So when you look at the subbasin hydrograph plot, at the bottom, you also see the rainfall or precipitation hydrograph pattern in the upper area. And you can kind of see this is, I think, an actual historic event. You can see a double peak in the runoff. Well, there's also kind of a double peak in the precipitation, so that matches. What other reason, forget about the precipitation, but why else would you maybe see a double peak in a runoff hydrograph? Well, you may have two drainage areas contributing, and they both may have different timing and large enough peaks that it shows up as a double peak. And so this is a plot at a junction, and so it shows every single hydrograph entering that junction, and then the hydrograph leaving that junction. And then here we have, you can see flow. There's an elevation. This is a reservoir in this case. All right, so just to let you know, like the model name information, like if you're copying your models over from Windows. All right, so the data storage system, again, we won't get into this too much, but you can open specific DSS files and do some different graphing and editing with them. At this point, we're going to go do a demonstration, but let's go ahead and take a break, and then we'll come back. I'll demonstrate the model, and then we'll jump into some hands-on workshops.